Hi, I'm Chris White. I teach music theory over at the University of Massachusetts Amherst in the United States. We're going to talk about a metrically based generative system of harmony today. So when we investigate harmonic grammars, usually we tend, and this is very logical, to just investigate chord transitions. And there's lots of people in my bibliography, including myself, that get at harmonic grammars by just looking at what chords move to what other chords. But what if some portion of harmonic grammars are caused or influenced by other parameters? What if the creative act of composing particular chord progressions is a fallout of other musical considerations? So, for instance, meter and accent seem to affect composers' harmonic practices, and they affect listeners' tonal perceptions. So, what if the ways that harmony supports metric accents determines, or at least determines aspects of harmonic grammars? What if harmonic syntax is actually just a fallout of the way pitch content expresses meter? What if harmonic syntax is just a fallout of the way pitch content expresses meter? So today what I'm going to do is show differences in chord changes that accompany relatively weakened strung pulses in tonal corpora. I'm going to show you that stronger pulses tend to host more pitch class change, and that different types of chords occur on stronger versus weaker pulses. I'm going to create a generative model using these corpus-derived properties, and then I'm going to compare and contrast the output of that model to chord progressions that are observed within actual corpora of music, as well as to baseline and expert models. And now the spoiler is that the metric model will heavily overlap with corpus-based tonal models. So to the first of these things, the harmonic changes that accompany metric pulses within some corpus. For my corpus, I use all of the tonal pieces in the Music 21 corpus that are also in XML format. So this will be the pieces by Bach, Beethoven, Mozart, Haydn, Verdi, Schumann. For consistency, I only use pieces in quadruple meter. I only use major mode pieces, and I transpose everything to C, and I only use the first 8 measures so that we don't have to deal with modulations. So how do I pre-process these? Each piece is divided into every moment that a pitch is added or subtracted from the texture. The XML file's metric data is then associated with each of those events. So a note comes on, and it's associated with one of 5 metric pulses. It's either at the beginning of a measure, at a half measure, on a beat between those, at a subdivision, or at the subdivision. So the beat would correspond to the quarter note pulse in a measure of 4/4, but the downbeat of the 4/4 measure would be the downbeat pulse. The half note halfway through the measure would be the half measure pulse, but then the quarter notes in between those would be the beats. The eighth notes in between those beats would be the subdivision. The 16th notes between those would be the subdivision. And I have more precise descriptions in the proceedings. But let me show you. The first question that we're going to ask is how many pitch classes change on different pulse levels. So if we looked at that 8th note, we'd be talking about the subdivision, because it's the 8th note that comes between 2 quarter note pulses. So this subdivision introduces one new pitch class, and that's G, and it retains one pitch class, C. So notice that the C holds over in the right hand there, and it introduces one new pitch class, G. So we would say at that subdivision there's one new pitch class. If we looked here, we would be comparing what's occurring on the 4th beat of the measure to the 3rd beat of the measure. So the previous beat's the 3rd beat, the current beat's the 4th beat, and we would say that that beat introduces one new pitch class, G, but it retains one pitch class, E. So that E in the left hand is the same, there's also an E in the right hand in the previous beat. And so that means that there's a retained pitch class. And we could do the same thing for the measure, where the second measure's downbeat introduces two pitch classes compared to the previous measure's downbeat, and there's no retained pitch classes. So if we graph this and we see what the average change in pitch classes is between adjacent pulses of various strengths in the tonal corpus, we would see that the measure, half measure, and beat all sort of are around 37-ish% of pitch classes retained between consecutive pulses. But then there's this jump at the beats subdivision and the subdivision subdivision. And these differences are significant according to a two-sided t-test. So what we learned from this is that so construed, more pitch classes are retained on metrically weak pulses than on metrically strong pulses. Stronger pulses seem to hold over fewer pitch classes than metrically weak pulses. So the second aspect of the corpus analysis is that I found that different chords tend to occur on stronger versus weaker pulses. So if we just ask what kinds of chords occur on different pulses, we could refine that a little bit by saying what scale degree sets appear on different pulses, what scale degrees onset, what scale degrees start on different pulses. So if we asked, hey, on that pulse, which is the half measure there, what scale degrees start there? Well, it's the set CE, and in C major that would be Do and Mi. But if we moved over one and we asked at that subdivision there, well, only G starts there. And that's scale degree 5, scale degree So in C major. So we can plot this and say what proportion of things happens on the beat pulse, the measure pulse, and the subdivision pulse. And 1, 5, 4 chords happen most frequently on the beat and the measure. But then if we look at the subdivision, what sorts of things start on subdivisions? Well, it tends to be singletons, like scale degree 4, Fa, scale degree 2, Re, scale degree 5, So. Very different things start on subdivisions as opposed to beats and measures. In particular, 1, 4, and 5, or C, F, and G major triads in the key of C major, tend to occur on strong pulses more than on weaker pulses. So now that we've identified these trends, let's generate some chord progressions using those trends. So I'm going to create a model using these metric/corpus-based logics, but I'm going to compare them to other models to see how they perform. In particular, I'm going to create models from published corpora of chord transitions. I'm going to create some baseline models, and I'll create a model using three-function syntax as taught in contemporary music theory pedagogy. So I'm going to pull something out of the music theory classroom to also test our model against. And I'll generate transition matrices using each of these models, and I'm going to correlate the matrices to identify similarities and differences between them using Spearman's rank coefficient. So I'm going to create all these models and see how similar they are to one another. So first, the metric model, the thing that we've been talking about, the thing that we're going to pull from these corpus-based preferences. So we're going to assume two pulses of alternating strengths. And the thing is that the corpus has already shown us how to fill these pulses in with chords. So we're going to populate with triads. Triads because we're just going to assume triads for simplicity's sake. And we're going to use the corpus-based preferences. So strong to weak transitions. When we go from a strong beat to a weak beat, we're going to change 1 or 0 pitch classes. When we go from a weak to a strong beat, we're going to change 2 or 3 pitch classes. So we're going to change more pitch classes when we're moving from a weaker to a stronger beat. Strong pulses are more likely to be 1, 4, and 5 chords in our model. So that's C, F, and G triads in C major. And weak pulses are more likely to be anything else. So we create this model and we will populate the alternating pulses, 100,000 alternating pulses with chords using these rules. And then we will compile a two-dimensional transition table from those 100,000 pulses. The formalization and transition matrix can be found in the proceedings. So let's just make sure we have our minds wrapped around this. So we're assuming a alternating strong and weak pulse. So that means on the strong pulse, we'll change pitch classes. On the weak pulse, we'll retain them. But also, we're going to prefer C, F, and G on strong pulses and not prefer them on weak pulses. So if we started with a C major triad, that means the second pulse could be an E minor triad because it would retain two pitch classes, and it wouldn't be a C, F, or a G triad. And then we would move to an F major triad because that changes all pitch classes. And then we could end with an A minor triad that holds two pitch classes. So this is the kind of chord progression that we're generating here. So the established corpus-based models that we're going to compare this to. So we're going to use 4 published chord transition matrices derived from corpora of analytic annotations. So 2 are going to be drawn from Western European common practice art music. So first I'm going to make a Casca-Payne model. And this is derived from Roman numeral analyses of the Casca-Payne textbook. David Temperley uses this all the time. And it just says how frequently in the Casca-Payne instructor's manual each Roman numeral moves to each other Roman numeral. I'll use the Tomasco model, which comes from Roman numeral analyses of selections of Bach, Beethoven, and Mozart. This is in Tomasco's 2011 book. But again, it shows how frequently each triad moves to each other triad. I'm going to restrict data to triads, diatonic scale degrees, and the major mode for simplicity's sake. I'm also going to use 2 from popular music. And that's going to be the de Klerk-Temperley, which is Roman numeral analyses of the 500 songs, greatest songs of all time, and the Hook Theory corpus, which are chord annotations from tens of thousands of American popular songs online that they allow you to scrape. Again, triads, diatonic scale degrees, major mode. I said that I would make a baseline. The baseline is a frequency-only model where we produce triads based only on their frequency of occurrence within the Bach chorales. I generate 100,000 chords using these frequencies and then make a transition matrix. So the rule-based model, the classroom-based model, the music theory model, it's from the Riemannian 3 functions, which is used by plenty of music theory writers. It's very ubiquitous in music theory scholarship. There's 3 syntactic categories or chord functions: tonic, subdominant, and dominant, and they look like this in C major, where your tonic function has your 1 chord, your C major chord, your 6, and your 3, your A minor and your E minor. That the E minor overlaps with the dominant function, which is mostly G major chords but can have E and B in it, and then your subdominant, mostly F, but can have A and D in it. So the rule-based model has all functions progressing to each other or to themselves, but dominant chords are twice as likely to produce tonic, to progress to tonic as to subdominant. That's kind of one of the hooks of this theory. And functions are twice as likely to generate their eponymous primary triads as their ancillary minor or diminished triads. So the dominant function is more likely to produce the G major chord, the dominant chord, than E or B. So that's the rule-based model. It also generates 100,000 chords, and I compile a transition table from those 100,000 chords. Now that we've got these models and these transition tables that describe them, let's correlate them and see what's similar to what else. The first thing that I want to draw your attention to is that the 2 common practice models, the 2 Western art music models, correlate really well together. The Tomasco and Casca-Payne both describe the same historical era, and they correspond really well. The same thing with the Hook Theory and de Klerk models. The 2 pop rock models correlate well. The frequency-only model doesn't really correspond to anything. This is the baseline model. It doesn't correlate to anything well, except it does correlate highly to the rule-based system. And the rule-based system correlates pretty well to the metric model, actually. But the rule-based model doesn't correspond to actual common practice models. So it doesn't predict what's going on in tonal corpora particularly well. But the metric model actually does. The metric model corresponds pretty well to each corpus that it predicts, that it correlates to. So let's discuss this. The metric model corresponds highly to a basic three-function pedagogical music theory rule-based model, but that rule-based model doesn't actually correspond to what happens in corpora, to corpus-based models of triadic syntax. The metric model, however, does. It does correspond to these corpus-based models of triadic syntax. The metric model, however, does not correspond as well as does other corpus-based models of the same style. So you have pop music model looking at another pop music model. It's going to be higher than the metric model looking at the pop music model. So the intra-style comparisons are higher than the metric model comparisons. So let's summarize for a second and then spin out. So we created a model that tracks the pitch class change and core type usage of strong and weak pulses as observed in some tonal corpora. We found that more pitch class changes and 1, 4, and 5 chords tended to occur on stronger pulses. When we made a model that does this, the model approximates tonal syntax, but this approximation isn't as robust as intra-style comparisons, pop music to pop music, common practice to common practice. But this means that the metric model potentially represents a baseline preference for certain chord transitions that's modified in different historical styles. The metric model potentially represents a baseline preference. So certain kinds of chords tend to occur on strong beats as opposed to weak beats. And those transitions seem to be held in common between different historical styles. So the metric model also, from another perspective, the metric model also approximated a traditional three-function model. But this rule-based three-function model, this music theory classroom model, did not approximate what happened in corpora. It did not approximate corpus-based models. So it's possible that the rule-based model, that the three-function system illustrates what Garrett Wiggins has called the folk psychology of music theory, the folk psychological nature of handed-down music theory. So the Riemannian classroom theory might describe an underlying trend within metrically ordered music to produce harmonic grammars that group chords by maximal pitch class overlap, and that then distinguish these between beats and between syntactic groupings via minimal pitch class overlap, or something like that. That the rule-based model is getting at something that's going on that the metric model actually gets at better. We can spin out even further and say that these results suggest that meter may have a fundamental impact on the ways that chord progressions are created. So variations within and between styles, like between the common practice and pop music, variations there might show a creativity associated more with metric than harmonic forces that you might be playing with meter when you change harmonic syntax, more than you're actually changing what we traditionally think about as harmonic grammar. So these findings, we could also imagine them adding a depth to the ways that composers play with harmonic and metric frameworks. So for instance, if pitch class change indicates metrically strong accents, then there exists a playful, subtle, and indeed a creative hemiola at the end of the first phrase of God Save the Queen. So bum 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 ba-dum bum 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 ba-dum bum 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 bum. A good old 3/4 jaunt there. But if we looked at the pitch class change, you've got a pretty clear hemiola at the end. So it would be bum 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 according to the pitch class change. And this is a kind of neat little creative usage of this trend which we've identified. Thanks so much for letting me talk to you. Thanks for arranging this, to Robin and Simon, and thank you so much for your attention. And I'm happy to take any questions, and I will post this video on my website, and I look forward to any comments you might have.